Hello, thanks everyone for coming. This is exciting. So I'm going to give like a lightning introduction, like less than 10 minutes, to TensorFlow Probability, which is our framework for probabilistic inference built on top of TensorFlow. And then I'll kick it over to Dustin, and he's going to tell a bit about his recent work. And then we'll go back to me. I'll talk a little bit about Gaussian processes, which is a little closer to my main project. So TensorFlow Probability is an open source Python library built on top of TensorFlow, making it easy to combine deep learning and probabilistic models on modern hardware. We have some R-like capabilities, ever growing, and we make it easy to do research combining deep models with models of uncertainty. So the idea is you, by using probabilistic models, can describe the structure of your problem more richly, and using our framework, you can perform inference in those models. So you have some domain expertise. You want to be able to express that and make models that are less generic than linear regression. So we have a bunch of tools in our toolbox that are designed to kind of fit together like Lego blocks, and we'll run through some of the lower level ones here. So the idea is you build your model and you do inference. We have some tools for building models and some tools for doing inference. And we'll probably focus mostly on distributions and bijectors here, given the amount of time we have. So our distributions library has something like, 60 or 70 distributions at this point, quite a few. Each distribution has roughly the same API. It supports sampling, measuring of probabilities and log probabilities, CDFs, survival functions, summary statistics where possible, and some methods for comparison, cross entropy, and this has a footnote at the bottom, this sort of fundamental concept of shape. So this is what allows us to vectorize operations and do things really efficiently. So we'll talk a little bit more about that. The two main kinds of shape that we think about are event shape and batch shape. So event shape is something like the dimensionality of the space that your distribution is defined over, right? So like a normal distribution is maybe over a one-dimensional variable. So that would be an event shape of scalar. Whereas a multivariate normal distribution would be vector variate and would have an event shape of, say, whatever the number of dimensions is. And then, matrix variate distributions like Wishart will have an event shape that is n by n or something like that. Batch shape allows us to have multiple independent and not necessarily identically distributed distributions that are batched together in the sense that we can perform computations in parallel on hardware which supports that. So here's a very simple example of creating a distribution, a normal distribution. The idea here is we've created a batch of two normal distributions, one centered at -1 and one centered at 1. And the scale for both is 1. And that, so ultimately the batch shape is 2. And the scale broadcasts, so if you're familiar with broadcasting in NumPy, our distributions all work naturally with that. So when you draw a sample from this distribution, what you actually get is two samples, one from each of the two distributions. And when you measure the probability of that sample, you'll actually get the probabilities of those two independent draws according to those two separate distributions. Again, these are like Lego blocks. You probably don't need to completely parse this slide, but the idea is that we have a bunch of different pieces that all fit together really nicely. Here we're taking a bunch of multivariate normal diagonals. We're creating a mixture distribution across them, and then we're using this independent kind of meta distribution to make them into one big joint model. Recently added addition to the library was the support for generalized linear models. So this is a nice, quick example of logistic regression, just really a handful of lines of code. And we have a nice second-order optimizer for fitting these. It's similar to GLM-net in R. We also recently added Gaussian process support. I'll talk a little bit more about this later. But this is an example of, again, in just a handful of lines, doing Gaussian process regression and sampling a bunch of draws from the posterior. And then let me touch on bijectors real quick, and we're already at 10 minutes in, and then I'll hand it over to Dustin. So bijectors are this idea of creating diffeomorphic mappings between spaces distribution supports. So the idea is you start from something simple like a normal distribution, and if you can map that smoothly and invertibly through some potentially very complicated mapping, you can express much richer distributions. And by having computationally efficient forward and inverse maps, as well as Jacobians for tracking the warping of the probability space, we can do efficient sampling as well as density estimation. So you can basically take a simple distribution like a normal, pass it to a transform distribution along with a bijector. Here we're using something called a masked autoregressive flow, which is nifty and fancy, but it's kind of like an invertible neural network, and so then you can train the parameters of that mapping and get really rich representations. And totally separate paper, we just invert that distribution, and it's a one-line change. So we run through a use case. So here's just kind of, this is way too much information to go through in detail, but you express your probabilistic model, and then we have tools for doing MCMC and other inference techniques on that model. So again, lightning introduction to TensorFlow Probability, and I'll hand it off to Dustin.
Hi. So just to get started, does anyone happen to know who these two figures are? Oh, no, of course. I pulled these from Wikipedia. So the first one is Edward I from King Edward, and the second one is King Edward II. Of course, this is sort of a play. I did not choose the name of the library based on rich old white people. It was named after a statistician. But this is sort of the theme of this talk, which is a transition in my lessons I've learned over developing probabilistic programming and sort of the research applications that have been motivating a lot of this stuff. So if you're interested in deep learning systems research, this is not that talk. If you'd like to hear more about that, so you can go to this probabilistic programming conference on Friday. I think the registration has been limited already, but the talks will be recorded, so you can probably go online and watch them. So to start stuff off, I always like to begin with some motivating applications in my own research. So in the first one that we've been doing, this was back in my PhD with a bunch of people in Dave Bly's group. We were really interested in just doing heavy exploratory data analysis, where typically what people do is just take a subset of data, run some GLM, do some basic understanding of the data set, and then they do like real analysis, And so what we wanted to do was really take this sort of philosophy of probabilistic modeling to heart, which was that instead of just having this data set and taking subsets, what we would do is really posit probabilistic models that are very simplistic. They're just describing sort of assumptions that you would usually make. In this case, it's sort of like probabilistic PCA, some form of dimensionality reduction, and we applied it to the full data set immediately. And we ran, using probabilistic programming frameworks like Stan, a scalable inference algorithm on it, and we got some results. We looked at it, we looked at the various mixture components, and so on and so forth. Another application we were interested in is population ecology, where we wanted to really understand these time series that evolved over very long dynamics, and they had these very complex differential equations involved in their rates of change. And so what we did was we considered various new forms of models as well as different forms of inference algorithms, and we did all of that using Edward, the probabilistic programming system. In another application, we're also just interested in better understanding of perceptual data. So one thing that we wanted to do was better compression algorithms and better generation of natural images. And so we've been exploring a lot of things that have been combining neural nets and probability distributions. And one that is also very near and dear to my heart has been just better models and inference algorithms for GWAS, where you're really interested in cause and effects of, say, a collection of SNPs down to a subset of traits. And in a paper that we did for ICLR, one of the deep learning conferences, we really just took causal models with neural networks and really showed that these things can significantly help both to understand better confounders, such as population effects, as well as just better regression fits for, say, features to traits or whatnot. And finally, one thing that we were interested in was just better spatial analysis in, say, basketball data. So we got this data set from Ryan Adams and his group, and we just used Edward, the probabilistic programming system, to just understand the landscape of inference algorithms and how different ways of approximating a posterior distribution in a model could really affect the downstream results you care about. And really to motivate probabilistic programming and these sorts of applications, I like to think of two different extremes. And then one of the extremes, you can take this sort of like AI generalist philosophy where there's this hypothesis that like everything from the universe is really a simulation of a computer program, and that like everything that you're really doing in data analysis is just like things that live in the computer and things that you're trying to approximate with something that's computable. In other words, that can be represented in bits and with finite computation with a program. And if this hypothesis was true, then what we're doing with data analysis with like programs and software is trying to approximate that computer program. And whenever we're analyzing little slices of this with science, we're just understanding the capacity of this really large Turing machine. I don't know if I really buy that argument, but that's one extreme. The other extreme is just about understanding better abstractions and software. If you were doing probabilistic modeling today, what are the sort of frameworks that you would use? What sort of software tools, and how would you scale these things up and connect with different hardware? So what I'm showing you here are just a bunch of repositories for different forms of research in building models and algorithms. And what they've done is they typically silo it off into their own little repository. You may have done this in your own work. And after they, say, publish a paper, it's sort of not really maintained anymore because it's hard to. It's all just various forked GitHub repositories. And so what we'd really like to do as a system is think of the way we build on science, of progressing on frameworks and baselines, continuing to do that process, and to do so in a way that's reified in software, not just what we say in words. Now, one of the things that we like to advertise in probabilistic programming is this way of specifying models and doing a form of automated inference. That all you have to do is specify the program that describes something like a generative process, which is your probability distribution that you're ultimately interested in, and using this sort of one-line API of like, I'm going to query and get my posterior distribution, and given that, I can do all sorts of predictions and downstream analysis that I want. And the myth of probabilistic programming is really that this way of style for programming just tends to be infeasible in practice. A core operation in language, namely that way of doing inference, is just so difficult that to do this in practice, you really have to think of a way of designing the system to enable something that's a little bit more flexible and more compositional in the way you do training and prediction and all that sorts of stuff. And so Edward was really designed to handle this process. So to go over some little pieces of Edward 1, which I worked on a few years ago, and many of the core ideas remain true to this day, the core piece of it is really this language that we're defining in building on top of TensorFlow, which is just the computational graph framework. And so in particular, what we did was we defined this notion of a random variable, which is really just a TensorFlow distribution, as Chris described, but with an additional notion of a tensor. So you can think of each random variable as just distributions augmented with some notion of a tensor that's based on sampling from that distribution. And so by sampling from that distribution, you can form calculus on the random variables, and you can form a language around this. And so in particular, one example of this is just the classical sort of state space model, where you might imagine that there is an emission matrix which defines hidden state to observations, as well as the transition matrix. And through these lines of code, it's defining through discrete time dynamics and very simple linear transitions how you go from initial states z0 all the way down to your observations over a sequence of steps. And of course, given this little snippet, you can always think of different extensions, such as changing the linear transition to be, say, deep neural nets, or thinking of different ways of handling the latent dynamics. For example, if you wanted a global variable that everything was conditioned on, that can disentangle the sort of latent state dynamics and the global dynamics and all that sorts of stuff. And all those sorts of things were sort of motivation for why we wanted something that was a little bit richer and compositional. And of course, on top of just the language was the sort of the minimal part. It was really about doing forms of inference. And so what we defined in Edward 1 was this taxonomy of inference algorithms, where there was a base class inference, everything was derived under this, and we could specify all forms of approximate posterior distributions using variational inference, which is just a fancy name for optimization algorithms, and Monte Carlo, which is doing a form of sampling as the main primitive of computation. And as we've been applying these tools for a lot of the research applications that I've described before, you came into a bunch of different failure modes, and we had to go back to the drawing board on a lot of these different parts. And in particular, one of the problems that we really faced was that the inference algorithms that I showed you is actually, it tends to be fairly monolithic. And in particular, the average workflow requires really understanding an entirely new ecosystem. In order to change to something like Edward and probabilistic programming systems, you have to make a bit switch in your head to really change the way you think. And that tended not to work well for a lot of users, and I think that was a way of stagnating adoption. Another thing that we're generally interested in, as we're always interested in machine learning, is just getting things to run faster and more scalably. And in particular, Edward, when we designed this, it was not really designed with TPUs and multiple machines in mind. It was really oriented to, say, at most multiple GPUs, 8 GPUs, like P100s and V100s, and say a single machine, say like on your laptop that you can SSH into Amazon Web Server or something like that. That's at least how I ran all my experiments. And we really wanted to push this, given that we're especially at Google, we have all these supercomputers that we can access, and now apparently everyone has cloud CPUs they can use. So we'd really like to push that as well. And another thing that has been harped on a lot, which I also think is very important, is this form of dynamism. That when we're specifying these probabilistic models and algorithms, TensorFlow was really the language that we're specifying. We're building these computational graphs that follow this sort of multi-stage programming model of like, you specify the graph and you execute the graph, and that does all the training. One thing we would like to do is just have everything be staged in Python itself, just that you can just execute operations immediately as you specify the computation. So those are the things that we strived out to do in Edward 2. And the way we did this was really just to try to distill what we really thought of as like the core of probabilistic programming, and what sort of abstractions could we distill out that could then be useful for all sorts of things in TensorFlow land and neural network research. And so one of the things that we ended up keeping was this notion of random variables. And so the way that we specify the model language was just the same as Edward 1. It's just that we would wrap the the models, the probability distributions in these little Python functions. And so formally, you can think of any of these sorts of Python functions as reifying a computable probability distribution. And typically, these functions would take in inputs, which are certain things it conditions on. Say in linear regression, it would take features as input, and then the return values would be the outcomes. And that would usually represent the generative process of given features, what is the distribution of y given x? And the second component that we added to Edward was just this notion of tracing that's common in automatic differentiation. This is sort of a low-level detail that I think most users don't really need to care about, but it was sort of important in understanding what are the main pieces of probabilistic programming and what sort of things we should probably keep and other things we can throw away. And so tracing is really this fundamental tool that allows us to specify programs and then manipulate them a posteriori. So you can do things such as specify your probabilistic model, which expresses all your domain assumptions, and then you can fit this thing using all sorts of computational tools you'd like, such as variational inference, Monte Carlo, and also even think about different ways of configuring hardware, just that if you wanted to do, say, training on a huge collection of TPUs, say like 256 TPUs, which is stuff that we do to this day, and then throw it onto a testing platform with, say, like a limited budget, such as like mobile hardware or even something like 2 GPUs, then all that should ideally be possible if you just express your model once. And so the declarative platform that probabilistic programming allows you, and what tracing allows you to do with that manipulation, is to really allow that.
Can you say a little more on why tracing makes that possible?
So it's a little detailed. The main idea is that basically you have this call stack in your programs, and every time that you define a random variable that executes, but is also pushed onto this particular interceptor stack in this code snippet. And every time it's pushed to the call stack, the user actually has this availability to just intercept the computation. In other words, like stop executions on the call stack itself. And then by doing so, they can do things like, if I run the generative process in my program, then at some point in the continuation of the program, the execution of the program, I can stop it, compute, say, a log probability, and continue and then change another piece of the program, swap it out with, say, some other distribution, and then continue on and so forth. So for example, one thing that allows you to do is just swap, say, the prior distribution in a program with the posterior distribution. Doing so just tends to have better semantics using something like tracing. Yeah, sorry, go ahead.
Is there a mic I should use?
Yeah, I think I'm not sure this is on.
Yeah, super great question. I think the way I tend to think about it, like a simple case, there are more complex cases, is that often for these probabilistic models, you want to have both a generative model, something that lets you sample from this program, and also a log probability evaluator. One way of thinking about tracing is that tracing easily lets you get both those things for free. That by running essentially the generative process, you're keeping a trace of what happened, and then you can swap in objects and essentially derive a log probability program from that. So it's a form of kind of on-the-fly compilation.
That's a great answer. So as an example of some things that you can do in Edward 2, one of the things that we focused on was grammar, probabilistic models of grammars, where in this example here, one thing that certain machine learning researchers have worked on has been generating molecules, which are represented in this sort of like smiles string format, which is really this what do you think of as like a tree, where the nodes represent the actual data you observe, and the subtree, the higher level tree components represent the productions that end up at those observations. And to build a probabilistic model, what you really had to do was build a generative model over trees. And so what we did was we formulated this little program, and the way this program worked was that it started from the root node of this tree, this little smiles start symbol, and then it is propagated down forward And the way that this worked was it used complicated, well, not really complicated, it just used the while loop. I mean, it's control flow that's a little less intuitive when you start thinking of this in TensorFlow land, and especially when you intercept this computation to do training, things become a little bit more difficult. So that's an example of stuff. Another example that we have done has been just high-quality image generation, where we pushed existing state-of-the-art models over, say, low-resolution images, at least. And we used data parallelism, where we just scaled the batch size of these training procedures across huge TPU configurations, and we saw that naturally, as you increase the number of TPU chips, there's a linear scaling as you get throughput. So what I'm showing you here is examples per second on the y-axis and the number of TPU cores or chips as we increase them. And the optimal linear scaling here is that, like, if you double the number of TPU chips, you should double the number of examples per second. And that's something that we actually do see, which is nice. Another example that we have worked on has been the Newton sampler, which is this very powerful algorithm for doing Markov chain Monte Carlo, and works across many different hierarchical generalized linear models and regression sort of models. Using Edward 2, really just building on top of the hardware that that a lot of people have worked on, we've been able to utilize up to 8 GPUs and shown that these things, for large data sets at least, really do matter. And so one of the numbers that we got, which was just not really tuning that many hyperparameters, was getting this 100x speed up over, say, Stan, and I guess this is more than 7x, 25 so for PyMC3. And this is something that wasn't really possible in Edward 1 because this algorithm required a lot of dynamism that just was unintuitive to express. And to compare this to handwritten TensorFlow without the little probabilistic programming decorations on top of things, it had negligible overhead. That's sort of nice. So as a high-level summary, we designed this system that was really to accelerate research and to push onto this notion of Box's loop that was to enable this sort of model inference procedure. That was what Edward was named after. Edward is Box's middle name. And we've integrated this into TensorFlow and a lot of the different components of the ecosystem to really allow us to push both the dynamism and the modern accelerator pieces. And in current directions, what we've been doing has been pushing both the scale, where we're trying to get to 1 trillion parameter models. If you're not familiar with the state of the art, people have been, or we've been training roughly 20 billion parameter models and fitting these on terabytes of data. And we're trying to advance fundamental understandings of our generative models and our Bayesian neural networks for understanding uncertainty. And for that, I'll hand it over to Chris.
Cool. So I'm going to talk about Gaussian processes, but real quick, an addendum that I neglected to mention last time. This is the team. It's a bunch of people that have made some amazing contributions to TensorFlow Probability and continue to do so. So just wanted to give a quick shout out. I won't name everyone, but
I think we've grown a bunch since then, actually. And also, we're on GitHub, so we take pull requests. So if anyone wants to contribute feature, we welcome that.
Yeah, for sure. And yeah, so you can find, we have a sub-site on tensorflow.org now, tensorflow.org/probability, and our GitHub repo is at github.com/tensorflow/probability. It's a really exciting shift in how Google does software development, that we're able to push a lot of this stuff out to open source now. And so that's really exciting. So yeah, contributions welcome. And bug requests are cool. So how many people are familiar with Gaussian processes in some sense? Oh, awesome. I think in the announcement about this there were some references to some other talks that were longer and more detailed than I'll be able to be here. Can people read this? It looks like it might be kind of too small. We can fix that. So I'm really just going to have to give another kind of a lightning discussion of this. But so we just recently added some support for Gaussian processes in TensorFlow Probability. And I want to show a couple of examples of how we do that. So I may end up writing something on the wall, but I may just stick to my my Colab notebook here. So the idea with yeah, you don't like the wall of text?
No, but give this link to
yeah,
afterward.
Sure.
Put it on the website.
Sounds good. So I mean, down here there is actually there's code that we'll go through, but so yeah, so the idea with Gaussian processes, right, is to take kind of an infinite generalization. Thanks. An infinite dimensional generalization of a Gaussian distribution, so yeah, so you sort of have this is a whiteboard. All right. You know, so your typical normal distribution. You know, maybe you have some values y distributed.
Right, big.
Bigger? All right. Yeah, so in a typical one-dimensional Gaussian distribution, you might have y normal of some mean and standard deviation. In higher dimensions, you might have a vector of y1 through yn distributed. We might write like multivariate normal with again some mean vector and now some covariance matrix. So these are actually special cases of Gaussian processes, right? They're Gaussian processes where your index set is finite. A Gaussian process essentially is just an indexed collection of random variables. So a bunch of random variables that we can put a label on each one, such that any finite subset, the marginal distribution of any finite subset, has a multivariate normal distribution. So there's kind of an interesting effect that happens when you go from these finite discrete index sets to a sort of like a dense index set like the reals or some finite dimensional vector space Rn. Namely, if you have a two-dimensional Gaussian distribution, maybe with kind of this kind of a covariance shape, there's really no difference in I've written y, so let's call these y1 and y2, right? We could also kind of parameterize this as y1 and y2. We could switch them, right? And we'd end up with something like this. And there's nothing essentially different. We've just kind of relabeled things. The fact that we've identified one dimension with the label 1 and one dimension with the label 2 is not really essential. When you go into an infinite dimensional index set, now you've really got spatial structure between the points. And so what does that mean? It's like you have, maybe this is our index set, R, and given any set of points, the distribution of function values, or distribution, if we think of the GP as a distribution over functions, which I didn't really say, but that's what we think of it as, the values of draws at these 3 points will be a three-dimensional Gaussian distribution, and their covariance, the covariance between them takes into account their spatial separation. And that's manifested through a covariance function, which we usually write something like k of x prime, and there are some conditions on this. Basically, like a valid covariance matrix has to be positive definite, and this function has to be what we call positive definite for functions, which basically means that if you feed any finite set of points to it, it gives you a positive definite matrix. But so, yeah, this was just kind of something that occurred to me recently, was that the spatial relationship of the points here is sort of essential to describing the structure, the covariance structure of the GP. Whereas here, I mean, switching 2 points here would kind of break the space, right? We would be creating holes and things. Whereas shuffling these things around doesn't really make much
difference. Can you write down sort of the canonical kernel that gives you nice smooth functions?
Yeah. So like what we call in our library the exponentiated quadratic. It goes by many names. Some call it Gaussian, some call it radial basis function, some call it the squared exponential, right? But yeah, so this is k of x prime is going to be equal to some positive number times the exponential of minus the distance between x and x prime. This could be a vector distance, like an L2 norm, divided by some characteristic length scale. So this is a pretty. Did I miss something? Oh, so this is, sorry, yeah, you're right. You want the L2 norm squared, right? Yeah. So yeah, this is a sort of canonical kernel function. Thanks. There are many others, and I think I link in this collab, which is posted online in our GitHub repo, to David Duvenot's page, which is like a kernel cookbook, and it has a whole bunch of examples that are very nice.
In particular, with this kernel, the closer the points are, the more correlated, you can see the more correlated the function.
Yeah, exactly, right? It's going to drop off as the square of the, exponentially as the square of the distance between the 2 points. And so, points that are very close to each other are going to be more correlated, and points that are further will be less.
Well, that's kind of a property of all reasonable kernels that give smooth functions, right?
Yeah. So you're always having this spatial. Yeah, there are probably interesting counterexamples, but yeah. Cool. So that's a bit of the background, and so I just want to show some code that does this using TensorFlow Probability. And so yeah, I run through a lot of the kind of introductory stuff here in the text, which hopefully is self-contained and readable. Is this? Okay, thanks. Right, so we do some imports. We grab NumPy, TensorFlow, and a couple of sub-packages in TensorFlow Probability. And I'm going to generate some data from a sinusoid sine function, and I'm going to add a little bit of noise to it. That's going to be my training data. So I'm just going to get some scattered samples from this function, and the samples themselves are going to be noisy. And so yeah, here I'm generating the data. I'm generating 100 training points scattered across the line. And I create some TensorFlow variables. These will be trainable. I'm actually going to need to figure out what the characteristic length scale and this what we call an amplitude parameter that multiplies that on the left, as well as trying to estimate the observation noise. So I said these samples are noisy. How noisy are they? So these are all trainable variables. I create a kernel object, which is exponentiated quadratic, parameterized with these variables. I create a GP distribution with that kernel. Index points refer to the points in the index set, right? We said that a GP is a collection of random variables, any finite subset of which is Gaussian distributed. So this is my finite subset, what I call the index points, the points in the index set. So those are the locations of the observations. And then the noise variance is parameterized, again, by that trainable variable up above. I'm going to train those variables by maximizing the likelihood of the data under this GP model. I'm going to do that with an atom optimizer, and I'm going to minimize the negative log likelihood.
Sorry, were you going to specify the likelihood?
Sorry, the log likelihood is taken here from the GP. So remember from the previous talk, each distribution object gives us access to a log prob function, and we just hand it some data, and it tells us the probability of those data under that distribution. Does that make sense? Or do you guys, are you asking, like, what is the log prob definition for the GP? Yeah. Oh, so, right. So at this finite set of index points, the GP collapses down to just a multivariate normal. So in the background, this is basically building a covariance matrix by applying the kernel function to all these pairs of points, like this. And then parameterizing a multivariate normal distribution with this covariance matrix. And then taking the log probability is just the Gaussian PDF formula.
But is the...
So you're saying right there in the right that it says yi is normal. What if yi is not normal?
So this is basically saying that we're adding normal noise. So this is the noise on top of the observations. So yeah, in general, what makes this particular example work nicely is the fact that this is a conjugate model. The noise is Gaussian on top of a Gaussian process, and so we can do a closed form analytic expression for the. Well, we can still get the log probability pretty easily, but we can do posterior inference in closed form. But if it's not, then we need to resort to something like MCMC or expectation propagation or something like that. And I will soon publish an example. We have MCMC capabilities in TensorFlow Probability, and this all fits together really nicely. I just didn't put it together for this talk. But this is a great question. Yeah, if you don't have Gaussian noise, then your model is no longer conjugate, and posterior inference is no longer something you can just write down.
Can you still do like stochastic variational inference on it? If, let's say, you're building a graphical model, the GP is like a part of it. Then it feeds to some other things, and then you observe something which depends in a complicated way on some GP. Can you handle that with TensorFlow Probability?
Can you repeat the question?
Oh, yes, thank you. Sorry. Sure.
So the question is that you can use GP as a building block of more complicated models. So this is basically the model that you're describing here is just basically just a GP with some Gaussian noise. So the question is that if it's part of a bigger, complicated graphical model, how can we deal with that with TensorFlow Probability?
Please.
And one of the examples in Edinburgh that we have is a Cox process. A Cox process is like a Poisson process where there's a rate function. It's sort of like a generalization of the rate parameter in a Poisson distribution. What you specify for the rate function is a Gaussian process. So you're just putting more stochastic processes on top of stochastic processes. And in this, what we used was variational inference to infer the latent rate function using another Gaussian process. Because these are all distributions, that's sort of the nice part of it, which is like compositionality.
Thanks. Yeah, so there's been some semi-recent work on doing interesting variational tricks with Gaussian processes, and particularly in terms of scaling them up. So the dirty secret here of the Gaussian processes is that doing anything non-trivial means inverting that covariance matrix, and the covariance matrix is generally the size of the number of observations, wide and high. So that's inverting that scales as n cubed, and that's not great when you have a million data points. So a lot of recent methods are looking at variational approaches to solving that scalability problem. And on top of that, you can use alternative likelihoods. But yes, John.
The noise that you're adding here is Gaussian, so you're just pumping up the diagonal of this kernel, right? Is it handled differently than just doing that internally, or is that what you do?
No. It's basically like down here. When we do the inversion, we just add a little sigma squared noise. Yeah.
And other question: the log probability function. Should I think of this as like what I imagine is I have these points in the domain and the values of the function that I observe, and is the log probability referring to the log probability of at a different point in the domain observing another value, or is it something else?
Right. So in the part where we're optimizing the model parameters. Sorry. So the question was about whether we're talking about the probability of the observations or the probability of some held out data, right? And so in this case, for training the model parameters, for basically doing model selection, we're looking at the probability of the observed data, fixing that observed data, and optimizing the log probability of that. And then after we've selected the model parameters by maximizing that likelihood, then we're going to do the posterior inference to look at the predictive values at new points. Good question. So again, this GP boils down to a multivariate normal distribution. The event space, if you will, is going to be vectors of observed data at some finite set of index points. And so this observations is a big Y vector. We took 100 data points here, so it's going to be a 100-dimensional vector of the observations. And this log prob function is going to give us back a scalar, which is the log joint density of those observations at those particular index points for this kernel. Right, so we train that. I think I probably should have ordered my cells a little differently, but this is where we run the training, just running the train op and gathering log likelihoods, which I'll plot in a moment. Let's actually jump down and look at that. So this is training, converges pretty quickly, and then, yeah, so 1,000 steps, and this runs in, even on pretty humble hardware, it runs pretty quickly, a couple of seconds maybe. But that's because we only had 100 data points. But really, at every one of these 1,000 steps, we're inverting a kernel matrix, right? Because we're changing the kernel parameters, and then we have to compute a whole new matrix, and then we have to redo the computation, right? So this is why GPs can get expensive.
And during the grading set procedure, we're also backpropping through the Klasky factorization. Yeah, and during the training procedure, we're doing gradient descent, which backprops through the Klasky factorization, which is used in the log probability computation. Fortunately, you don't have to think about all that sort of stuff. It's just computing a log probability and then running an optimizer, just like you would do in TensorFlow.
Yeah, good point. Cool, so this was the result of training, and then the other thing we're going to do after that is we're going to build this is where we actually build the posterior. So this is the GP regression, where we regress some new points against the data we have previously observed. So now I'm going to provide some predictive index points, and here I'm actually going to fill a whole strip of the real numbers, of the real line, with a bunch of evenly spaced points. And now I want to say, give me samples from the posterior at all of these, jointly over all of these points, conditioned on the observations, right? So now I have a 200 by 200 kernel matrix for these 200 predictive points. So those are my predictive index points. I'm going to feed those to the GP regression model with the same kernel, reusing the same parameters that we just learned. And I'm going to give it locations of the observations that we want to condition on, as well as the observations themselves. And then I'm going to put predictive noise variance to 0, just because it makes a prettier plot. But if we actually believed that our data was noisy, we might want to noise that up. I'm going to draw 50 separate samples of these 200 points. And so the result is going to be 50 curves that should more or less trace through the data. And when we plot it, that's what we see. So the blue points are the noisy data, just a sinusoid plus some Gaussian noise. And the red kind of faint lines are the 50 samples drawn conditioned on those. So that is GP regression.
So your kernel was just the squared exponential, or did you also train parameters on a periodic kernel?
No, so we have an exponentiated sine squared kernel, which would be definitely more appropriate for this model. But I did the exponentiated quadratic. It works well where the data is, but you can see as soon as we get away from the data, it starts to go crazy. But if we had trained a periodic kernel, you would see basically that all of the samples would actually be periodic, perfectly periodic. So I've got 5 minutes left. I was going to talk about Gaussian process latent variable models, which is kind of another interesting angle on Gaussian processes, but I could also just take questions, or...
Well, are there any questions so far?
This may sound like somewhat of a silly one, but it's mainly just one thing that I think is...
This may seem like a bit of a silly one, but I think this has probably been the question that's probably come up the most often, because I've actually been trying out TensorFlow Probability for a few months now. And the one thing I suppose, it seems like there's differences between Edward 2 and like TensorFlow Probability, like there's things you could sort of use one or the other for. Is there like a TensorFlow probability equivalent for Edward or Edward 2's value method?
I guess, well, right. So Edward 2 kind of builds random variables on top of TensorFlow distributions, and it adds sort of two features immediately with respect to the value function, which is that if you don't provide a value when you instantiate an Edward random variable, it draws a sample. It implicitly creates a sample operation in the TensorFlow graph, or immediately samples it if you're in eager mode. And if you provide a value, then you're sort of clamping the variable to that value. So, those are features designed to be used in conjunction with tracing and doing different kinds of introspection of the generative model when you're kind of writing in the Edward paradigm. Under the hood, the sampling is backed by TensorFlow distribution sampling. So the value setting is a pretty Edward-specific thing that can be used for conditioning. Dustin, do you want to say any more? Did that answer your question, or?
Yep. Yeah, I think just because of time.
Yeah.
If you could, we can come back to this in discussion.
We'll come back to this one.
But I think people in the audience might be interested. We're not going to have time to go through more code probably, but
yeah.
What is the model that you presented this to that you were about to describe?
So the latent variable model, it's cool. So the idea there is basically, a traditional latent variable model might be something like PCA, which assumes a linear mapping from some latent variables to your observed data. And the GP latent variable model is basically a generalization of that allows for nonlinear mappings. Yeah, so you might have some high-dimensional data. In this example, I use MNIST digits. So I'm going to just zip right through all of the code that actually does stuff. And the idea is we're not going to be given the index points here. We're going to train the index points as variables in a TensorFlow graph so as to optimize, to maximize the likelihood of the observed data. So it's an unsupervised method. We're simultaneously going to optimize kernel parameters and observation noise. So kernel parameters, observation noise, and the index set. And we're going to find points in the index set that can be a low-dimensional latent representation of the observed data. So here...
The map generalizes the linear map. What kind of map is it then?
Well, that's a good question. I mean, in GP regression, it's these kind of waggly lines that are coming from conditioning on the data. It depends on the kernel. Is the kind of the short answer. Sorry.
It's a sample from a GP with some kernel.
Right. Yeah, so the idea is that the latent variable model is describing, Dustin?
Yeah, so in PCA, you can just think of it as like you have a normal distribution, and then you have a linear function of that normal distribution, and you have another normal distribution. That's probabilistic PCA. In GP LVMs, you just take that linear transition. You have a function. That function is then drawn from a GP. So the generative processes draw from normal distribution, draw from GP. That's my new function. I apply it to those normal inputs, get normal outputs. And that is a GP LVM.
Yeah, thank you. So yeah, quickly, this is the initialized. So I took MNIST digits, and I tried to come up with a two-dimensional latent representation of them. So this is where it started, just randomly initializing everything. Actually, PCA is the way you're supposed to initialize it, but I found that this did pretty well and kind of told a simpler story. And after training, which was like, I was expecting this to be a lot more complicated. It's like, I don't know, maybe 20 lines of code, and it trained in like about 100 iterations. It was really quick. And so each of these dots is a different MNIST digit, and the colors correspond to MNIST digit classes. And I haven't done a plot where I actually look at what each of the dots look like, but presumably there's like some 7s that look kind of like 1s next to each other here. And then we can even do posterior sampling, and it's not the best the best sample. Like a VAE would be much nicer than this, but this is basically a grid in that space of posterior samples from each point. And so, there's some things that look like digits there, which is pretty cool. Yes?
So do you have any code for probabilistic process in TensorFlow or your?
Right, so the question is whether we have code for Dirichlet processes, and I don't think we have anything explicitly. We do have, I don't think you published your example, right? Riff wrote some example code at some point doing a DP model. but we don't have anything explicitly in the library. The trouble there.
We have Dirichlet distributions, certainly.
Oh yeah. We have a finite dimensional Dirichlet distribution, yes. And so we have kind of the tools you would need to do some kind of like a finite projection of a DP. The problem is we generally have a limitation. We don't want things in our library that can run for an arbitrarily long time. And so we've been hedging on directly implementing infinite structures.
I guess rather than saying, I mean, normally if you look at some of the best methods for doing DPs in the literature, what you'll often find is that they cap the number of components at a fixed number and then do inference based on that. We could code that up fairly easily. We haven't done it, but it's not hard to write given the tools we have. It's much more painful to write something where you actually want to do sort of real inference over the number of components. That ends up not being a good match for TensorFlow, because usually in TensorFlow, at least classic TensorFlow, you're building a graph and you don't want to change the size of that graph at runtime. You want to have a fixed size graph. We're in the process of switching lots of stuff to TensorFlow Eager, which changes the story a little bit. But basically, there's a tension where things that are static in their sizes and their compute patterns are much easier for us to deal with than on-the-fly dynamicism. And there's kind of a deep tension there that relates to how you make stuff that runs effectively on GPUs and accelerated hardware. So we're still working through the best answers. But certainly some work with Dirichlet processes is possible for us.
One final question?
No, we got one. Oh. Sorry, we'll have some more chance to talk.
Is there any support for like survival models, censoring, and so on?
I'm sorry, can you repeat it?
Is there any support in TensorFlow probability for survival models like censoring, right censoring, Weevil distribution, or something like that?
Probably one of my colleagues can answer that better than I can. We have a bunch of distributions and sampling methods. Today, you'd probably have to roll your own, but we have some great tools to do that.
Well, thank you so much. Thanks to the speakers for this great talk.